Welcome to Deep Ocean Sleep Science. Tonight, we embark on our most ambitious documentary journey, a some-minute exploration of the Mariana Trench, Earth's deepest natural sanctuary. This film is crafted with a singular purpose: to guide you into deep, restorative sleep through the gentle understanding of oceanic science. We will move slowly, speak softly, and frame every discovery not as dramatic revelation, but as peaceful knowledge settling into your consciousness like sediment on the ocean floor. The Mariana Trench represents more than just a geographic extreme. It is a philosophical space where our planet's most fundamental processes become visible. Where immense geological forces meet biological resilience. Where darkness is not absence, but a different kind of presence. For the next, we will document its formation through Earth's tectonic rhythms, trace the history of human curiosity that sought to reach it, introduce the remarkable life forms that call it home, and explore the scientific principles that govern this hidden realm. Consider this: at this very moment, as you prepare for sleep, the trench exists in perfect stillness 11,000 meters below the Pacific surface. Its conditions remain constant: the same pressure, the same near-freezing temperature, the same profound silence that has persisted for millions of years. That same constancy, that same deep, rhythmic stability, is what we invite into your rest tonight. Just as the trench remains undisturbed by surface storms, your mind can find a depth undisturbed by daily thoughts. If this documentary helps you find the profound peace you seek, consider joining our community of deep-sea sleep explorers by subscribing. Your support allows us to continue creating these extended journeys where ocean science becomes a pathway to rest, and where documentary becomes meditation. Now, settle into your most comfortable position. Imagine the gentle weight of water above you, not as burden, but as comfort. Our documentary begins with geography. The Mariana Trench forms a graceful, crescent-shaped arc in the western Pacific Ocean, approximately 200 kilometers east of the Mariana Islands. Its coordinates place it between 11 degrees and 20 degrees north latitude, and 142 degrees to 147 degrees east longitude. This places it within the Ring of Fire, the circum-Pacific belt of volcanic and seismic activity that encircles the ocean basin, home to 75% of the world's volcanoes and 90% of its earthquakes. To appreciate its scale, let us employ gentle comparisons. If we placed Mount Everest, at 8,848 meters tall, into the trench's deepest point, its summit would remain submerged under 2,146 meters of seawater. The Grand Canyon, while majestic, measures approximately 1,857 meters at its deepest. The Mariana Trench is nearly 6 times deeper. Another comparison: if the trench represented the height of a 10-story building, the deepest parts of most oceans would only reach the second floor. The trench's discovery belongs to the HMS Challenger expedition of 1875. This British research vessel, on a pioneering global oceanographic survey, deployed hemp ropes weighted with cannonballs. When their sounding line reached 8,184 meters, a depth previously unimaginable, they realized they had found something extraordinary. The expedition's scientists, led by Charles Wyville Thomson, carefully recorded temperatures, water samples, and marine life at various depths, establishing modern oceanography. They named the deepest sounding Challenger Deep, a name that endures. Think of early depth sounding like lowering a weight on a very long string until it touches bottom. Today, we use multi-beam sonar, sound waves that paint a detailed picture of the seafloor through precise timing of echoes. The trench exists because of plate tectonics, the slow, graceful dance of Earth's crustal plates. Here, the Pacific Plate, ancient, dense, and heavy, meets the younger Mariana Plate. Rather than colliding, the Pacific Plate bends downward, beginning a descent into the mantle at an angle of about 30 to 45 degrees. This process, called subduction, occurs at about 2 to 8 centimeters per year, roughly the speed your fingernails grow. Over 50 million years, this movement equals approximately 4,000 kilometers, the distance from New York to Los Angeles. This subduction carves the trench over millions of years. As the plate descends, it generates deep focus earthquakes, up to 700 kilometers deep, and volcanic activity in the Mariana Islands above. The trench is thus not a static scar, but an active, living feature of our dynamic planet. The descending plate also carries seawater into the mantle, which influences volcanic activity and helps regulate Earth's long-term water cycle. As we contemplate these vast timescales, let your own sense of time expand. The worries of today, the pressures of this week, they are momentary compared to these geologic rhythms. Let them sink away like sediment settling through miles of water. The surface water above the trench is remarkably deep blue and clear, fed by currents like the North Equatorial Current and the Kuroshio Current. This surface world teems with life, flying fish skimming waves, dolphins playing in bow waves, seabirds like albatrosses gliding on updrafts. But our documentary journey turns downward now, leaving this sunlit realm behind. We are like a piece of marine snow beginning its long, slow descent to the abyss. Approaching sleep is like approaching the trench's edge. You leave behind the bright, busy surface world of conscious thought. You prepare to descend into the deeper layers of your mind, where different rules apply, and a different kind of peace resides. The transition from wakefulness to sleep mirrors our departure from the sunlit zone into twilight. And so, we begin our descent, leaving the memory of sunlight above us, like closing our eyes at day's end. A documentary of the deep must honor its layered nature. The ocean is not uniform, it is a stack of distinct environments, each with its own physics, chemistry, and biology. Our descent passes through these zones like turning the pages of a deep, blue book, each chapter revealing new adaptations to increasing pressure and decreasing light. The first 200 meters constitute the sunlight zone, epipelagic. Here, photosynthesis is possible. Phytoplankton, microscopic plant-like organisms, form the base of the ocean food web, capturing solar energy through chlorophyll. A single liter of surface water may contain millions of these tiny beings. This is the ocean's bustling metropolis, home to most familiar marine life, tuna, sharks, sea turtles, and the great whales. But already, pressure increases. At just 10 meters down, pressure is double that of the surface. Your body would feel this as a slight squeeze on air spaces, ears, sinuses, but for marine life, it is simply home. Many fish have swim bladders filled with gas that they must adjust as they change depth. As we sink to 100 meters, the world turns monochromatically blue. Water absorbs colors selectively, reds and oranges vanish first within the first 10 meters, then yellows by 50 meters, leaving only blues and violets that can penetrate deeper. This is why underwater photographs require artificial light to restore color. The blue light that remains has a calming, tranquil quality. Studies show blue environments lower heart rate and blood pressure. The mind can relax into this blue monotone, letting go of visual complexity, much like dimming lights before sleep. We cross into the twilight zone, mesopelagic, 200 to 1,000 meters. Sunlight here is reduced to a faint, dusky glow insufficient for photosynthesis. This is the realm of the Deal vertical migration, the largest daily migration of biomass on Earth. Each night, countless organisms, krill, squid, lanternfish, ascend hundreds of meters to feed near the surface under cover of darkness, descending again at dawn to avoid predators. This movement moves an estimated 10 billion tons of carbon daily through the water column, a vital ecological pump that sequesters atmospheric carbon in the deep sea. Life here adapts to low light. Many creatures have large, sensitive eyes. Some, like the opa or barrel-eye fish, have tubular eyes fixed upward to detect silhouettes against the faint surface light. The barrel eye has a transparent dome protecting its upward-facing eyes, while it can also rotate them forward. Others begin to exhibit bioluminescence, the biological production of light through chemical reactions involving luciferin and luciferase enzymes. At 500 meters, the pressure is 50 times surface pressure. The last vestige of sunlight fades to near darkness. The temperature drops significantly to about 10 degrees Celsius. We encounter the permanent thermocline, a layer where temperature decreases rapidly with depth. This creates a density barrier that can trap nutrients and sound waves. Many submarine sonar systems exploit this layer, as sound waves bend along it, allowing detection at great distances. Some whales, like the sperm whale, dive through this layer to hunt giant squid in the darkness below. We enter the midnight zone, bathypelagic, 1,000 to 4,000 meters. No sunlight penetrates here. This is eternal night. Pressure is now 100 atmospheres. Yet, this darkness is alive with bioluminescent displays. An estimated 90% of deep-sea creatures produce light. They use it to communicate, attract prey, like the anglerfish's lure, camouflage themselves with counter-illumination, matching downwelling light to erase their silhouette or startle predators. The colors are usually blue or green, as these wavelengths travel farthest in seawater. Is a private, silent fireworks show that has continued for eons. Food is scarce. Organic matter, marine snow, drifts down from above, dead plankton, fecal pellets, dust. This slow, constant snowfall is the primary food source for many. Some creatures, like the vampire squid, have adapted to this scarcity with the lowest metabolic rate of any cephalopod and efficient feeding structures. It can turn its webbed arms inside out to form a pineapple posture when threatened. Other inhabitants include the gulper eel with its enormous mouth, and the fong-toothed fish with proportionally the largest teeth of any marine species. The abyssal zone, abyssopelagic, 4,000 to 6,000 meters. We are now on the abyssal plain, vast, flat regions of sediment-covered ocean floor covering about 50% of Earth's surface. Pressure, 400 atmospheres. Temperature, 2 to 3 degrees Celsius, near freezing. Life here is even slower, more energy efficient. Sea cucumbers, brittle stars, and grenadiers move with deliberate slowness. Hydrothermal vents and cold seeps create isolated oases of surprising abundance, powered not by sunlight but by chemosynthesis. At cold seeps, methane and hydrogen sulfide seep from the seafloor, supporting tube worms, mussels, and bacterial mats. The conditions here begin to approximate those we will find in the trench. Chemosynthesis is like photosynthesis, but instead of using sunlight, bacteria use chemicals like hydrogen sulfide or methane to create energy. These bacteria form the base of entire deep-sea food webs, independent of the sun. This discovery in 1977 revolutionized our understanding of where and how life can exist. We cross the final boundary, 6,000 meters. This is the Hadal zone, hadal-pelagic, named for Hades, the Greek underworld. This zone exists only in trenches and deep troughs. Less than 3% of the ocean floor is hadal, but it includes our destination. Pressure exceeds 600 atmospheres. The temperature is consistently 1 to 2.5 degrees Celsius. We are now entering the Mariana Trench proper. The Hadal zone is fragmented into isolated trenches, each potentially hosting unique species adapted to its particular depth and geography. The Mariana Trench is the largest of these, creating the deepest ecological niche on Earth. With each zone we pass, let go of a layer of waking consciousness. The bright, active surface mind, the twilight of drowsiness, the deep, dark quiet of approaching sleep. You are sinking through your own psychological zones, each deeper than the last, each more restful. This descent mirrors the stages of non-REM sleep. The light sleep of stage 1, the sunlight zone, where you're still aware of surroundings, the deeper relaxation of stage 2, the twilight zone, with sleep spindles and K-complexes protecting your rest, the slow wave sleep of stages 3 and 4, the midnight and abyssal zones, with delta waves like the slow currents of the deep, and finally, the profound, restorative depths we are about to enter, akin to the deepest, most healing phases of sleep. The abyssal plain now slopes downward, the trench walls begin to rise around us, channeling our descent into ever deeper realms. Our documentary now focuses on the feature itself, the architecture of the deep. The Mariana Trench is a geomorphic marvel, a testament to Earth's dynamic nature. Its dimensions speak of grandeur, approximately 2,550 kilometers, 1,580 miles, long, roughly the distance from New York City to Las Vegas. Its average width is 69 kilometers, 43 miles, though it narrows to about 40 kilometers at its deepest point. It is not a narrow crack, but a vast, sweeping valley that could contain multiple Grand Canyons. Its deepest point, Challenger Deep, is located near its southern end within a smaller basin called the Challenger Deep Valley. The trench's cross-section is asymmetric, reflecting its tectonic origin. The western slope, on the Mariana Plate side, is gentler, with an average gradient of about 7 degrees. The eastern slope, the subducting Pacific Plate, is steeper, averaging 15 to 20 degrees, often characterized by fault scarps and slumped terraces where sections of the slope have collapsed. The walls are not bare rock, but covered in fine sediment, clay, silt, and the microscopic calcium carbonate shells of plankton called foraminifera, that has settled over eons like a gentle, continuous snowfall. The sediment is incredibly fine and easily disturbed. When submersibles land, they often create benthic storms, clouds of silt that can take hours to settle in the still water. This sediment is an archive, holding records of climate change, volcanic eruptions, and even cosmic events in its layered composition. Scientists can extract core samples and read them like tree rings, revealing Earth's history over millions of years. The sediment also contains nodules of manganese and other metals that form incredibly slowly, over millions of years, through precipitation from seawater. Pressure is the trench's defining physical characteristic. At Challenger Deep's 10,994 meters, the pressure is 1,086 bars, or 15,750 pounds per square inch. To conceptualize this gently, it is equivalent to one person supporting the weight of 50 jumbo jets, or the pressure you would feel if you balanced the Eiffel Tower on your thumbnail. Yet, this pressure is uniform, applied equally from all directions. For an incompressible object, like one filled with water, it is not crushing, but embracing. Organic tissues, being mostly water, can withstand these pressures if they lack air spaces. Pressure is force per unit area. In the trench, the force is the weight of an 11-kilometer high column of water pressing down. But because water transmits that pressure equally in all directions, Pascal's principle, a fluid-filled organism feels squeezed evenly, not flattened. It's like being hugged from all sides simultaneously. Temperature remains remarkably stable, between 1 degree Celsius and 4 degrees Celsius, 34 to 39 degrees Fahrenheit, throughout the Hadal zone. This cold is constant, unchanging. There are no seasons, no daily fluctuations. This thermal stability is another aspect of the trench's profound constancy. The cold actually increases water density, which affects how sound travels and how creatures' metabolisms function. Enzymes in trench organisms are adapted to work optimally in this cold, high-pressure environment. The geology is active. The subducting plate carries water, as hydrous minerals, deep into the mantle, which lowers the melting point of rock and generates magma. This fuels the volcanic Mariana Islands arc above. Mud volcanoes and seeps on the trench floor release fluids and gases like methane and hydrogen sulfide, supporting unique microbial communities. These seeps are often surrounded by white mats of bacteria that oxidize the chemicals for energy, forming the base of localized food webs. Sound behaves uniquely here. The extreme pressure increases water density, which increases the speed of sound by about 4% per 1,000 meters depth. The SOFAR channel, sound fixing and ranging, a depth layer where sound travels farthest with minimal loss, extends into the trench. A whale's call or an earthquake's rumble can travel for thousands of kilometers through this deep-sea channel. The trench's shape can also focus sound, making it audible at great distances. This is why hydrophones placed in the deep ocean can detect earthquakes and whale songs from halfway around the world. The impression was that of an infinite, timeless, dark wilderness, a place utterly removed from the world of light and life. Yet, in that profound isolation, there was a peace I had never experienced, a silence so complete it felt like a physical presence. Paraphrased from Don Walsh's Reflections on the Trieste Dive. We are now in the deepest 1,000 meters of the trench. The water is supremely clear, almost devoid of suspended particles because the immense pressure compacts everything and because there's little current to stir up sediment. It is a clarity born of extreme compression and stillness. The silence here is not an absence of sound, but a purity of it. Only the very lowest frequencies, the Earth's own hum, microseisms from waves and tectonic activity, persist. This environment has remained stable for geological time, allowing life to adapt incrementally over millions of years. The trench's constant cold, immense pressure, and profound silence are like the ideal sleep environment, cool, weighted, and quiet. Your body seeks these same conditions: a cool room, around 18 to 20 degrees Celsius, the gentle pressure of blankets. Weighted blankets are therapeutic, the silence of night, to achieve its deepest rest. Just as the trench's stability allows specialized life to flourish, a stable sleep environment allows your body to perform its essential restorative functions. Feel that constant coolness. Not as a chill, but as a soothing, stable temperature for your thoughts. Feel the gentle, all-encompassing pressure, holding you in stillness, like the deepest, most comforting hug. Hear the deep silence, allowing your mental chatter to settle like sediment in still water. This extreme environment is not empty. It has been visited, however briefly, by humans and machines driven by insatiable curiosity. Our documentary now turns to the history of that exploration, the story of how we reached for the deepest point. Human exploration of the Mariana Trench is a story of incremental progress, technological ingenuity, and profound courage. It begins in earnest in the 20th century, as we developed vehicles capable of withstanding the crushing pressures of the deep. The first manned descent to Challenger Deep occurred on January 23, 1960, aboard the bathyscaphe Trieste. This unusual vessel, designed by Swiss scientist Auguste Piccard and later acquired by the U.S. Navy, was essentially a heavy sphere attached to a large float filled with gasoline for buoyancy. The pressure sphere, just 2.1 meters in diameter, was made of forged steel 12.7 centimeters thick. Inside, Swiss oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh endured a 4-hour, 48-minute descent into darkness. During their descent, they faced a critical moment when a window crack propagated, causing loud noises. They continued, reaching the bottom at 10,916 meters, later revised to 10,994 m. They spent 20 minutes on the bottom, observing the seafloor through viewports. They reported seeing a flatfish, likely a sea cucumber, and shrimp, proving life existed even at these extremes. Their ascent took 3 hours, 17 minutes. This dive set a human depth record that stood for 52 years. As we landed, a cloud of sediment rose like a ghostly veil. We turned on the outside lights, and there, in the beam, was life, a pale, flat fish resting on the bottom. That moment changed everything we thought about the deep sea. The next major chapter was unmanned. From 1995 to 2003, the Japanese robotic vehicle Keiko made multiple successful dives to Challenger Deep, collecting sediment and biological samples. Keiko was a remotely operated vehicle, ROV, connected to a surface ship by a fiber optic cable. In 1995, it recorded a depth of 10,911 meters and captured the first video of the trench floor. Tragically, Keiko was lost during a typhoon in 2003 when its connecting cable broke. The torch passed to American technology. In 2009, the hybrid ROV Nereus reached Challenger Deep, diving autonomously, without a tether, for most of its journey. It broadcast live video from the bottom and collected samples. Nereus was lost in 2014 during a dive to the Chromatic Trench when it imploded under pressure. The next human visit came in 2012, when filmmaker and explorer James Cameron piloted the deep-sea Challenger to Challenger Deep on a solo mission. Cameron's vertical submersible, nicknamed the vertical torpedo, was engineered with syntactic foam for buoyancy and a pilot sphere made of steel 6.4 centimeters thick. The descent took about 2 hours, 36 minutes. He spent approximately 3 hours on the bottom, collecting samples and filming with 3D cameras before his hydraulic system issues prompted an early ascent. Cameron described the landscape as desolate and alien, comparing it to the moon's surface. He noted the profound isolation and the constant awareness of the immense pressure just centimeters away. His expedition collected 68 new species and provided high-resolution mapping data. Since then, several other vehicles have reached Challenger Deep. In 2019, American explorer Victor Vescovo's limiting factor submersible made multiple dives, including the first manned descent to the deepest point of the Sirena Deep, another deep spot in the Mariana Trench. His 5 Deeps expedition systematically visited the deepest point in each ocean. Modern deep-sea submersibles use materials like titanium or ceramic for pressure spheres, which are stronger and lighter than steel. They're designed to compress slightly under pressure, which actually makes them stronger, like an egg in your palm. Today, exploration continues with autonomous underwater vehicles, AUVs, and landers, untethered devices that free fall to the bottom, conduct experiments, then drop weights to return to the surface. These are more cost-effective and can stay deployed for months. International collaborations, like the Japan Agency for Marine Earth Science and Technology, JAMSTEC, and the Schmidt Ocean Institute, continue to push boundaries. Future missions aim to establish permanent observatories on the trench floor to monitor seismic activity, climate signals, and biological communities in real time. Exploration history mirrors our own journey into sleep. At first, we may approach rest with trepidation, early attempts. With practice and the right conditions, technology, we learn to descend more smoothly. Sometimes we encounter disturbances, like equipment issues, but we persist. Eventually, we reach the deepest, most restorative states. Each night's descent builds on previous experience, just as each expedition built on prior knowledge. Consider the courage to descend into the unknown. Tonight, you embark on your own descent into sleep, a journey you've made many times, yet each time is a new exploration of your inner depths. Trust the process, as the explorers trusted their vessels. Having traced how we reached this place, our documentary now introduces the permanent residents, the remarkable life forms that thrive where humans can only visit briefly. Life in the Mariana Trench challenges our understanding of where and how life can exist. The inhabitants here are not monsters, but masters of adaptation, each a testament to evolution's creativity under extreme constraints. They exhibit what scientists call hadal adaptation, a suite of traits allowing survival at depths below 6,000 meters. Let us meet some of these remarkable beings, starting with the simplest forms. Xenophyophores are single-celled organisms, but unlike any cell you've imagined. They are giants, reaching up to 20 centimeters in diameter, the largest single cells on Earth. They construct intricate, delicate houses called tests from particles gathered from the sediment, gluing together minerals, sand, and even their own waste to form beautiful, labyrinthine structures. They move slowly across the seafloor, extending pseudopodia, temporary projections, to capture food particles. Scientists consider them ecosystem engineers because their tests provide microhabitats for other small creatures like nematodes and copepods. Next, the scavengers, hadal amphipods. These crustaceans, relatives of beach fleas, exhibit gigantism in the trench, some reaching over 30 centimeters long. In shallower waters, amphipods are typically millimeter-sized. Here, freed from certain predators and possibly due to colder temperatures, which can lead to larger body sizes in marine invertebrates, they grow enormous. They swarm bait placed on the seafloor, consuming carrion that sinks from above. Their exoskeletons are fortified with aluminum compounds extracted from sediment, making them stronger to resist pressure. The champion of vertebrates, the Mariana snailfish, Pseudoliparus swirei. Discovered in 2014 at about 8,000 meters, it is the deepest living fish known. This small, about 30 centimeters, translucent fish appears delicate but is supremely adapted. It lacks a swim bladder, which would collapse. Its skull is not fully closed, with openings to balance internal and external pressure. Its bones are thin and flexible. Its cells produce high levels of a compound called trimethylamine N-oxide, TMAO, which stabilizes proteins under pressure. TMAO levels increase linearly with depth across fish species, a beautiful example of biochemical adaptation. The unseen majority, microbial life. Bacteria and archaea thrive in trench sediments, sometimes reaching densities of 10 million cells per cubic centimeter, comparable to coastal sediments. Many are piezophils, pressure-loving. Some consume methane or hydrogen sulfide from seeps. Others break down the toughest organic compounds, like chitin and cellulose, that sink from above. Their enzymes work efficiently under high pressure and cold, attracting interest for industrial applications like laundry detergents that work in cold water. Then there are the holothurians, deep-sea cucumbers. In the trench, they are often the largest mobile animals. They move slowly, ingesting sediment to extract organic matter. Some species have elongated, delicate tentacles for feeding. Their bodies are mostly water, making them less affected by pressure. They play a crucial role in bioturbation, mixing sediments and recycling nutrients. Bioluminescence persists even here. While less common than in midwaters, some trench inhabitants produce light. Possible sources include prey lures on anglerfish, though no anglerfish have been recorded from full trench depths, defensive flashes, or bacterial symbionts. The darkness is so complete that even the faintest glow can be effective. Adaptations extend to the cellular level. Trench organisms have fluid cell membranes with higher proportions of unsaturated fatty acids that remain flexible under pressure. Their proteins have more charged amino acids on their surfaces, interacting with water to maintain shape. Some have multiple copies of pressure-sensitive genes to ensure adequate production of essential proteins. Imagine proteins as intricate origami shapes. High pressure wants to crush them. TMAO acts like a supportive scaffold, holding the shape intact. It's like having a friend steady your hand in a strong wind. Life here is slow. Metabolic rates are estimated to be 10 to 100 times slower than surface counterparts. A trench amphipod might live for years, growing slowly. Reproduction is likely infrequent, with fewer, larger eggs. These are strategies for conserving energy in a food-poor environment. But how do they withstand the pressure? The key is equilibrium. Since their cells are mostly water, which is incompressible, and they lack large air spaces, the pressure inside and outside equalizes. They don't feel the pressure in a painful way, they are acclimated from conception. Eggs and larvae develop under the same conditions. It's their normal. The Hadal Zone is not a biological desert, but a reservoir of unique biodiversity shaped by isolation, pressure, and geological activity. Each trench may host endemic species found nowhere else. Perhaps most intriguing is what we haven't found. An estimated 85% of the trench remains unexplored. New species are discovered on nearly every expedition. There could be larger creatures, different ecological relationships, even novel biochemical pathways. The trench holds mysteries that may rewrite biology textbooks. These creatures exemplify elegant adaptation to extreme conditions. Similarly, your body adapts beautifully to the extreme state of sleep. Your brain waves change, your breathing slows, your temperature drops, all optimal adaptations for restoration. You are as perfectly suited for sleep as the snailfish is for the trench. Imagine yourself as adaptable as these creatures. Not resisting the conditions of sleep, but flowing with them. Your body knows how to do this. Your cells know how to restore themselves. You are designed for this deep, restorative state. These biological marvels exist because of the trench's unique physics and chemistry. Our documentary now examines the scientific principles that make this possible. The Mariana Trench is a natural laboratory for extreme physics and chemistry. Understanding these principles helps us appreciate not only how life survives there, but fundamental truths about our planet. Let us explore these gently, as one might ponder concepts while drifting towards sleep. Hydrostatic pressure is the increase in pressure with depth due to the weight of overlying water. It increases by approximately 1 atmosphere, 1 bar, 14.7 psi, for every 10 meters of descent. At Challenger Deep, this means 1,086 times surface pressure. This pressure affects everything: the density of water, the solubility of gases, the behavior of sound, and the functioning of biomolecules. Interestingly, pressure increases the viscosity, thickness, of water slightly, making it about 30% more viscous at the trench bottom. Gas solubility increases with pressure. Gases like oxygen and carbon dioxide become more soluble in cold water under high pressure. This means trench waters are often oxygenated, supplied by cold polar waters that sink and spread along the seafloor. Oxygen minimum zones occur at mid-depths, not the bottom. Thus, trench creatures are not oxygen-starved, they live in cold, oxygen-rich water. Think of pressure forcing more gas molecules into solution, like pressing a sponge into water until it's fully saturated. The cold also holds more gas. So the deepest waters are rich in oxygen delivered from the poles. Protein stabilization under pressure is a key biochemical challenge. Proteins, the molecular machines of life, have precise three-dimensional shapes essential for function. High pressure can distort these shapes. Trench organisms combat this by accumulating piezolites like TMAO, as mentioned, and by having protein structures with more ionic bonds and compact folding. Some enzymes actually require high pressure to function optimally. They are piezophilic. Membrane fluidity is maintained by altering lipid composition. Cell membranes become less fluid under pressure and cold. Organisms incorporate more unsaturated fatty acids, with kinks in their chains, to keep membranes fluid. It's like using a different oil in a cold engine to prevent it from gumming up. Sound propagation is fascinating. Sound speed depends on temperature, pressure, and salinity. In the trench, the cold tends to decrease sound speed, while high pressure increases it. The net effect is a minimum sound speed at around 1,000 meters depth, the SOFAR channel, below which speed increases again. Low-frequency sounds can travel enormous distances with little loss. The trench is surprisingly noisy with geological sounds, earthquakes, landslides, and the calls of whales that travel down from above. Geochemical gradients occur at seeps and vents. Where fluids escape the seafloor, sharp gradients of chemicals like methane, hydrogen sulfide, and ammonia create energy sources for chemosynthesis. Microbes form the base of food webs, oxidizing these chemicals with oxygen or nitrate. These ecosystems are independent of sunlight, analogous to how life might exist on icy moons like Europa. Time perception in a featureless environment is an interesting concept. With no day-night cycles, no seasons, and minimal environmental change, how do trench organisms regulate their biological clocks? Some may use internal circadian rhythms. Others may respond to tidal cycles, pressure changes of a few percent as tides rise and fall, or to the timing of marine snowfalls, possibly seasonal at the surface. For humans in submersibles, time can feel distorted, minutes stretch, hours compress. Cosmic ray penetration is an unexpected factor. The water column provides shielding from cosmic radiation. At the trench bottom, radiation levels are about half those at the surface. Some scientists speculate that life may have originated in the deep sea, protected from early Earth's intense UV radiation. Pressure effects on evolution are profound. The Hadal zone is fragmented into isolated trenches, each a potential island for speciation. Genetic studies show that populations in different trenches are often distinct species, having adapted to their specific depth and conditions. The trench thus acts as an evolutionary crucible, driving the creation of new life forms. Your body undergoes its own extreme adaptations during sleep. Brain chemistry shifts, GABA increases, cortisol decreases. Cellular repair mechanisms activate. Memories consolidate. Just as trench life adapts to physical extremes, your biology adapts to the physiological extreme of sleep, a state equally vital for survival. Consider the elegant physics of your own body. Your heartbeat, your breath, the electrical signals in your brain, all following natural laws, just like the principles governing the trench. There is intelligence in this design. Trust it. The trench does not exist in isolation. It is connected to the broader Earth system in profound ways. Our documentary now explores these connections. The Mariana Trench, despite its remote depth, plays integral roles in Earth's functioning. It is a node in planetary systems that affect climate, geology, and even the chemical composition of the oceans. First, the carbon cycle. The trench is a significant carbon sink. Organic matter produced at the surface, phytoplankton, dead animals, waste, sinks as marine snow. Much is consumed in mid-waters, but a fraction reaches the abyss. In the trench, sedimentation rates are relatively high due to its topography trapping particles. This organic carbon gets buried in sediments, sequestered from the atmosphere for millennia. Subduction may even carry some carbon into the mantle, completing a long-term carbon cycle that regulates Earth's climate over millions of years. Second, plate tectonics and seismicity. The trench is where the Pacific Plate begins its descent. This subduction generates earthquakes, including megathrust earthquakes that can trigger tsunamis affecting coastlines around the Pacific Rim. Studying the trench helps us understand seismic risks. Instruments placed on the trench floor monitor strain accumulation. The slow bending of the plate also releases fluids that hydrate the mantle, influencing volcanism in the Mariana Islands arc. Third, nutrient and ocean circulation. Deep waters formed in polar regions sink and flow through the trench as part of the global thermohaline circulation, the Great Ocean Conveyor Belt. This circulation redistributes heat and nutrients worldwide. The trench's depth influences these deep currents, potentially creating upwelling zones that bring nutrients back to the surface, supporting fisheries thousands of kilometers away. Fourth, biodiversity and bioprospecting. Trench organisms possess unique biochemical adaptations. Their enzymes, piezozymes, work under high pressure and cold, interesting for industrial processes like food processing, brewing, and pharmaceuticals. Compounds from trench microbes are being screened for antibiotic and anti-cancer properties. The trench is a reservoir of genetic novelty that could benefit humanity, highlighting the importance of conserving these unexplored ecosystems. Fifth, climate records. The sediment layers in the trench archive Earth's climate history. By studying cores, scientists can reconstruct past temperatures, greenhouse gas levels, and volcanic activity with high resolution. This helps predict future climate changes. The trench's stability preserves these records exceptionally well. The trench acts like Earth's basement archive, storing records of past climates in layered sediments, much like tree rings or ice cores. Sixth, planetary science analog. The conditions in the trench, high pressure, cold, chemosynthetic ecosystems, are analogous to those suspected on icy moons like Europa and Enceladus. Studying how life thrives here informs the search for extraterrestrial life. NASA uses deep-sea exploration as training for space missions. Environmental concerns must be mentioned calmly. Even the trench is not untouched by human activity. Microplastics have been found in trench organisms. Chemical pollutants like PCBs exist in trench sediments. The potential for deep-sea mining for rare earth elements poses a threat. International treaties are being developed to protect hadal zones as unique, fragile ecosystems. The trench reminds us that everything is connected. What we do on the surface eventually reaches the deepest depths. Just as the trench supports surface life through interconnected systems, your deep sleep supports your waking life. It regulates hormones, cleanses metabolic waste from your brain via the glymphatic system, consolidates memories, and repairs tissues. The deep, unseen processes of sleep are as vital to your health as the trench's processes are to planetary health. Feel your connection to this larger system. Your breath is part of the planet's atmosphere. Your body is mostly water, cycled through oceans over eons. Your rest is part of nature's rhythm. Having explored the trench's science and significance, we now turn inward. Our documentary concludes with a personal descent, an invitation to internalize this journey. Now, imagine yourself not observing, but experiencing. This final segment is an invitation to internalize the trench's qualities, to find your own challenger deep within. Close your eyes gently if you haven't already. Picture yourself descending. Not in a submarine, but as a consciousness sinking through layers of your own mind. Each layer you pass represents a concern, a thought, a memory from the day. Let them go, like marine snow falling away into darkness. Feel the pressure increasing around you. Not as oppression, but as a deep, comforting embrace. The weight of the day is being held by something vaster than yourself. You are supported completely. There is no need to hold yourself up anymore. Notice the temperature, a cool, constant freshness. Like the cool side of the pillow that soothes your mind. The fever of busy thought settles into a calm, stable clarity. Hear the silence. Not emptiness, but a rich, full silence, the sound of pure presence. In this silence, mental chatter loses its power. Words dissolve into sensation. Thought becomes feeling. You are reaching your deepest point. Your personal challenger deep. Here, there is only being. No doing. No problem solving. No planning. Just existence in its simplest, most peaceful form. In this depth, imagine the trench's residents around you, not as frightening creatures, but as companions in stillness. The graceful snailfish, flowing with pressure. The patient sea cucumber, moving slowly through sediment. The microbial mats, quietly transforming energy. They are all masters of their environment, and in this moment, you are too. This depth within you is always available. It is your innate capacity for profound rest and restoration. You carry it wherever you go, just as the trench lies always beneath the Pacific. Now, very gently, begin your ascent. Not rushing, but rising slowly, gradually, carrying this deep calm with you. Feel the pressure lessen so subtly you barely notice. The darkness softens. You return through the layers, but transformed. The peace of the depth remains in your cells, your breath, your being. You are returning to the surface of consciousness, but you bring the trench's gifts, stability, resilience, and the knowledge that profound peace exists within your own depths. Our documentary journey concludes as we break the surface, not with a splash, but with a smooth, seamless emergence into moonlight. We have explored the Mariana Trench together, from its geographic setting to its exploration history, from its mysterious inhabitants to the science of its extremes. We've seen how this deepest place is not a frightening abyss, but Earth's most profound sanctuary of calm, a realm where pressure becomes embrace, darkness becomes rest, and silence becomes peace. Remember these lessons as you drift into sleep tonight. That pressure can be comforting when it's uniform and expected. That darkness can be peaceful when it's a natural state. That life adapts beautifully to its conditions, and so can your mind. That the deepest places often hold the greatest serenity. This has been Deep Ocean Sleep Science's documentary on the Mariana Trench. We create these extended sleep journeys to combine the wonder of science with the restorative power of guided relaxation. If this experience has brought you value, please consider subscribing to our channel. By subscribing, you join a community of deep-sea sleep explorers and ensure you never miss a journey into restful knowledge. Turn on notifications so you're gently alerted when we release new content. We also invite you to explore our other documentaries, The Midnight Zone, A Journey into Deep-Sea Sleep, Ocean Currents, The Flow of Rest, and Coral Dreams, A Reef Lullaby. Each is designed to guide you into deep, restorative sleep through ocean science. Thank you for spending these minutes with us. Thank you for trusting this journey. Wherever you are in the world, may the trench's eternal calm become your own inner peace tonight and every night. Good night, and may your sleep be as deep and as restorative as the Mariana Trench itself.